Swayam Prabha. Digital India. Educated India.
Good morning. We will continue with our discussion on surface patches. As you would note, we are on the third column of our course layout now. Today, I'll brief you with different models of surface patches, and I'll focus on only one of them, namely the tensor product surfaces. Today is lecture number 36. Design of surface patches. This is something that I have been repeating over and over again. The Jordan's curve theorem. A closed, connected composite surface represents the shape of a solid. This surface, in turn, is composed of surface patches, which is what we are going to be designing. Aesthetics, aerodynamics, fluid flow, etc. are many physical factors that would influence surface design. Surfaces of aircraft wings and fuselage, car body and its doors, seats and windshields are all designed by combining surface patches at the boundaries. Surface patches can be modeled mathematically in parametric form as a function of two parameters, u and v, which is written in ordered form, a row matrix comprising x as a function of u and v, y as a function of u and v as well, and z also as a function of two parameters u and v. The bounds for two parameters are between 0 and 1 each. X, y, and z are scalar polynomials or scalar fields in parameters u and v. There are different kinds of surface patches that we can design. The first one, which we are going to be focusing on in this lecture, is the tensor product surface patches. The second, which we will deal with later, is the boundary interpolating patches. The third one would be the sweep surfaces. And the fourth would be a class of quadric or analytic surface patches. Today, we'll be focusing mainly on tensor product surface patches. Now, what is a tensor product surface patch? Let's assume that phi and psi are two univariate functions such that phi is given by a set of functions phi I, all of them as functions of parameter u, the index I going from 0 to m, and psi is again a set of functions psi j, all of them as functions of v, the index j going from j equals 0 to n. Here, the values of parameter u belongs to a set capital U, which you have seen 0 and 1, and so is the case for values of the parameter v belonging to a set capital V, which again is defined by the interval 0, 1. Using these two function sets, we can define a tensor product surface R as a function of u and v as summation index j going from 0 to n, again summation index I now going from 0 to m, c sub ij phi sub I as a function of u times psi sub j as a function of v. This is the tensor product surface in the domain u times v, or u cross v. Here the coefficients c, I, j are all real variables and they belong to the Euclidean space. For example, the surface is bi-quadratic for m equals n equals 2 and bicubic for m equals n equals 3. Let's take a look at a case where phi I is given by a set of linear functions, phi 0 and phi 1. These linear functions are, for example, 1 minus u and u. 1 minus u is phi 0 and u is phi 1. And psi of v is a set of functions psi 0, psi 1 and psi 2, all of them as quadratic. For example, psi 0 is 1 minus v squared, psi 1 is 2v times 1 minus v, psi 2 is v squared. If you observe, these are linear Bernstein polynomials, each of degree 1, and these are quadratic Bernstein polynomials of degree 2. Using this model here, we can write R of uv as the ordered set of x, y, and z, which is equal to the row matrix 1 minus u, u, times the geometric matrix here C00, C01, C02, C10, C11, C12. These are the two rows in a matrix. And we'll have a column containing the functions psi j, 1 minus v squared, 2v times 1 minus v and v squared. Let's say, for example, that C00 is 0, 0, 0, C01 is 0, 2, 4, C02 is 0, minus 1, 3, C10 is 1, 2, 0, C11 is 1, 2, 4, C12 is 1, minus 1, and 3. These are, in a way, the x, y, and z coordinates. This is how the surface patch looks like. The curve in red corresponds to the values u as constant. The curve in black, which is actually a line, corresponds to v equals constant. If you observe, this line in black is being swept along this curve. To give us the tensor product surface. You can also think of this surface being a sweep surface, but we'll reserve our discussion on sweep surfaces for later. We can generalize and say that the tensor product surface R as function of u and v, the two parameters, can be given by summation j going from 0 to n, summation I going from 0 to m of d sub ij u raised to I v raised to j. D sub ij would be some constants in cases it would be or they would be unknown coefficients. This is equal to a row matrix containing all the u's, rather all the powers of u. For example, u raised to m minus 1 up till 1 times the coefficient matrix given by dmn dmn minus 1 up till dm0 in the first row, dm minus 1 n, dm minus 1 n minus 1 up till dm minus 1 0 for the second row. We can continue until we get the last row as d0n, d0n minus 1 up till d00. And this is followed by a column vector comprising all degrees in v. For instance, v raised to n, v raised to n minus 1 up till 1. Here, m and n can be user-chosen degrees in parameters u and v. They may be the same, they can be different. For example, for a bicubic surface patch, one would need to specify 16 sets of data as control points and or slopes. Y16 for a bicubic will have 4 rows and 4 columns. For each coordinate, we will be having 16 coefficients or variables. As I said, 1 for each d sub ij. Patches with degrees in u and v greater than 3 can be modeled. This generalization does not stop us from designing surface patches of any degree in parameters u and v. As I said before, one can as well choose the degrees unequal in the two parameters. But for most applications, use of bicubic surface patches seems adequate. Let's consider the first tensor product model, Ferguson's bicubic patch. This is given by R of u and v equals summation j going from 0 to 3, I going from 0 to 3, c sub ij, phi of I as a function of u and phi of j as a function of v. Here the two sets are the same that we use here. What do you expect these functions will be? Take a guess. Try also to recollect our discussion on Ferguson curves. Would you think these will correspond to the Hermite cubic polynomials? Yes, they would. Coming back to this tensor product model, we can write this in matrix form as phi 0 of u, phi 1 of u, phi 2 of u, phi 3 of u. This comprises the first row matrix times the 4 by 4 coefficient matrix. Remember that we will be using different coefficient matrices for different coordinates x, y, and z. The entries are C00, C01, C02, C03, C10, C11, C12, C13, and so on up till the last 4 by 4th term as C33. And correspondingly, we'll have a column vector comprising of the functions phi0, phi1, phi2, and phi3 in V. As I said before, Cij's will be ordered. Phi0 of u is given by 2 u cube minus 3 u squared plus 1. Phi1 of u is minus of 2 u cube plus 3 u squared. Phi2 of u is u cube minus 2u squared plus u. Phi3 of u is u cube minus u squared. Likewise, phi0, phi1, phi2, and phi3 as functions of V can be constructed. As we discussed before, these are Hermite cubic functions. Let's try to figure how we can determine the unknown coefficients Cij. Say we have a curve, we have another one, the third one, and the fourth one. These are 4 bounding curves for this Ferguson's bicubic patch. This one here corresponds to V equals 0. The u parametric direction is along this curve, let's say. This curve here corresponds to u equals 0. This one here for v equals 1. And the last one for u equals 1. Let's name different geometric attributes that are required to construct or to design the surface patch. The first point is r sub 0, 0. The second one is r sub 0, sub 1. Third one here is r 1, 0. And the fourth one is r 1, 1. The first index corresponds to the parameter u, and the second index corresponds to the parameter v. This is the best way to remember. You start at a point that corresponds to u equals 0 and v equals 0. Correspondingly, you identify this point as r sub 0, sub 0. If you move along the u direction, since this curve corresponds to v equals 0, you hit at this point, which corresponds to u equals 1 and v equals 0. And therefore, you can think of naming this point as r 1, 0. Likewise, if you move along this curve here, this is for u equals 0. This point here would correspond to values of u as 0 and v as 1. You can name this point as r 0, 1. Similarly, this would be r 1, 1. Now, these are only 4 of the 16 conditions that we need to completely determine this patch. How about the other 12 conditions. Remember that when discussing Ferguson segments, we were dealing with slopes. Let's consider slopes here as well. This is the slope along the u direction at this point. This is the slope along the v direction at r 0, 0. The slope along u, the slope along v. Slope along u, slope along v. The same for this point as well. Let's try to name these slopes as well. But before, let's identify the curves on this patch which would correspond to constant values of u and v. This curve here would correspond to a constant value of v. Try to observe this and this here, and this curve right here would correspond to a constant value of u. Now this slope is along the u direction, so we have r sub u here evaluated at u equals 0 and v equals 0. What is r sub u? It is partial r over partial u. Likewise, this slope here corresponds to partial r over partial v evaluated at u equals 0 and v equals 0. For this point r 0, 1, the slope corresponds to r u at 0 and 1, and this one here corresponds to r sub v at 0 and 1. The slope right here corresponds to partial r over partial u evaluated at u equals 1, v equals 0. The slope here is r v at 1 and 0. Likewise, these two slopes here are r u and r v respectively, evaluated at u equals 1 and v equals 1. What's next? Now, we have 12 conditions of the 16 that we want. We will have to generate 4 more conditions to be able to completely determine this patch. Let's recall this mathematical form for Ferguson's bicubic patch. R of uv equals summation j going from 0 to 3, I going from 0 to 3, c ij phi I of u and phi j of v. This was written in this form where we had a row vector comprising these Hermite functions, a column vector again comprising the Hermite cubic functions in terms of v, and then these unknown coefficients, which were 16 of them. Let's try to fit this information in the mathematical form and try to determine the unknown coefficients c I j. All we would need to do is, for the points, plug in the values of u as 0 and 1, plug in the values of v as 0 and 1, and determine maybe 4 of these coefficients. For the slopes along the u direction, we'll have to differentiate this expression with respect to u and plug in the corresponding information. For slopes along the v direction, we'll have to differentiate the same expression now with respect to v. We can determine 4 more of these coefficients. You can do the algebra all by yourself. Let me give you the results. So C00 is the first point, R00. C10 is R10, point corresponding to u equals 1 and v equals 0. C20 is the slope along the u direction at the first point. C30 is the slope again along the u direction at a point corresponding to u equals 1 and v equals 0. Likewise, C01 is R evaluated at 0,1. C11 is R evaluated at 1,1. C21 is the slope along the u direction evaluated at 0,1. C31 is the u slope evaluated at 1,1. C02 is RV00. C12 is RV10. C22 is RUV00. I'll talk about that in a moment. C32 is RUV10. C03 is the slope along the v direction at u equals 0 and v equals 1. C13 is RV11. C23 is RUV evaluated at u equals 0 and v equals 1. And C33 is RUV at 1,1. We had seen the information previously in terms of the points, the slopes along the u direction and the slopes along the v direction. These were 12 sets of information. Where did these come from? Well, since we are working with the slope information at the corner points, to generate 4 more conditions, we will need the mixed derivative information as well. This is what these 4 conditions pertain to. RUV is the mixed derivative of R with respect to u and v evaluated at u equals 0 and v equals 0. Likewise, RUV at 0,1, which is C23, is partial to R over partial u partial v at u equals 0 and v equals 1. RUV10 is C32, which is partial to R over partial u partial v at u equals 1 and v equals 0. And finally, RUV11, which is C33, this is equal to partial to R over partial u partial v at u equals 1 and v equals 1. So now we have 16 conditions, corresponding to which we can determine 16 unknowns. And then we have the Fergusson's bicubic patch at our hand, completely determined. Fergusson's patch is now given by this expression here. R of uv is equal to the row matrix comprising the Hermite cubic functions in U times all the C's now, all theCij's now, which are determined here, multiplied by a column vector corresponding to the Hermite cubic functions in V. I must have mentioned before that it becomes a little difficult for the designer to work with the slope information. That was a drawback with Ferguson segments, and it's also a drawback with Ferguson's bicubic patch. Let's consider some examples. But before that, I can write this complex looking right hand side in a very compact form as a row vector u. Recall what this was when we discussed Ferguson segments, times a matrix M times G times M transpose times B transpose. Now this corresponds to a row vector that contains the elements 1, u, u squared, and u cube. Likewise, this column vector will have elements 1, v, v squared, and v cube. You might want to figure the order in which they appear. M is the Ferguson coefficient matrix and G is the geometric matrix. So this is G and this is the Ferguson coefficient matrix that we had seen in case of Ferguson segments. I can subdivide this geometric matrix into 4 parts. This is the way I would remember the matrix G. This part here on top left corresponds to the point data 0, 0, 0, 1, 1, 0, 1, 1. So these would correspond to the coordinates at the 4 corner points of a patch. The submatrix on the top right would correspond to the V slope information, partial R over partial V. They will be evaluated in the same order as here 0, 0, 0, 1, 1, 0, and 1, 1. This submatrix here in the bottom left corresponds to the U slope information, that is partial R over partial U. Again, evaluated in the same order, U equals 0, V equals 0, U equals 0, V equals 1, U equals 1, V equals 0, U equals 1, and V equals 1. And this one here in the bottom right corresponds to the mixed derivative information. In CAD literature, this information has a name. Partial 2R over partial U, partial V are called twist vectors. Now for the examples. Let's look at a simple Ferguson bicubic patch. The geometric matrix is given by 6, 0, 0, 6, 0, 6, 0, 0, 6, 0, 0, 6, 0, 6, 0, 0, 6, 6, 0, 0, 6, 0, 0, 6. Looks like 6 happens to be a lucky number here. 0, 5, 0, 0, 5, 0. We have here 0, 0, 0. We represent this by a single number here. Likewise, 0, minus 5, 0, 0, minus 5, 0, 0, 0, and 0. Try to identify in this geometric matrix which ones of these entries would correspond to the points information, to the slopes along the u direction, to the slopes along the v direction, and to the twist vectors. As I said, we can divide this matrix into 4 subsystems. Draw a horizontal line here, draw a vertical line here. These entries will correspond to, you guessed it, the points information. How about these entries? They are the slopes along the v direction. At u and v as 0, u as 0, v as 1, u as 1, v as 0, and u and v both as 1. Try to remember this order. These entries are the slopes along the u direction. Again, evaluated at 0, 0, 0, 1, 1, 0, 1, 1. And of course, these 4 entries are the twist vectors. Now, as a designer, you would be comfortable specifying these 4 points. You may be okay satisfying the slopes along the v direction and satisfying the slopes along the u direction. Although I must mention that these numbers are not intuitive for all of us to specify. How about the twist vectors? It will be a little difficult for us to predict a shape for any given set of twist vectors. A totally non-intuitive information. So let's say we assign these twist vectors 0 values and try to see how a Ferguson's bicubic surface patch looks like. R of uv is given as capital U times capital M times capital G times capital M transpose times capital V transpose. You can do the algebra. I'll give you the final result here. So if I use only the first entries in these ordered sets, I'll get the scalar field in X. The field is 7u cube minus 13u squared plus 6. Even though the variable v does not appear here, this field is actually a function of u and v both. Likewise, if I consider the second entries or the second set of entries in these ordered sets, I would be able to compute the scalar field y of u and v. For this case, it's given as minus of 7u cube plus 8u squared plus 5. Finally, considering the third set of entries will give me the z uv field, which is 6v. This is, I emphasize, a very simple example. Now, this is how a Ferguson bicubic patch looks like for this geometric matrix. Let's experiment with this for a while. Let me change the twist vector arbitrarily. So here I have entries like 100, 0, minus 100, here minus 100, 0, 100, minus 100, 0, minus 100, 100, 0, 100. How would a patch look like? I could see a bulge somewhere at the center here. This bulge was not present here. But did I know that I would get such a change in the shape of the surface patch if I introduced non-zero values for these twist vectors? Maybe not. You can try with different geometric matrices to convince yourself that indeed predicting the shape of a bicubic Ferguson's patch by changing the v slopes, the u slopes, and the twist vectors may not be very easy. This gives us the motivation to study surface patches that involves only specifying design points or control points. Let's say as a designer we would not like to specify higher order information like the slopes, the twist vectors, second derivatives, third derivatives, and so on. With this said, we will try designing different tensor product surfaces that involve only design points, and we'll do that in subsequent lectures.